Alright, guys, here's what we got when we're talking about nuclear chemistry. Alright, so if something's undergoing alpha decay, which is represented by hopefully something that my pen will let me write, this, right? It looks about like that. What it's releasing is this right here, the helium nucleus, right? So it's releasing a total of 4 atomic mass units, 2 of which are protons. Okay. It's important to remember in nuclear chemistry, we're not going to pay attention to the pluses and minuses of the actual atoms themselves because you're just worried about the nucleus. That's the main reason that you are only talking about um, that you only worry about what's going on in the nucleus. That's why it's nuclear chemistry. We're not worried about the electrons at all. Okay, so we'll jump right into it. For radon, radon is it's Rn, I believe. Rn 198 in this case because of it says radon 198 and the atomic number 86. Yes. Yeah. Okay. So if that undergoes alpha decay, we are going to be left with something plus an alpha particle, right? Which is a 4,2 He. So we should know alpha decay equals this. This is going to be part of our reaction, right? So these have to equal the same number on both sides of the equation, just like when you're balancing an equation. Except for you have more numbers to pay attention to here, right? So 86 minus 2 is going to give us, stupid thing, not stupid, but 86 minus 2 is going to give us 84, right? And 198 minus 4 is going to give us 194. And so we'll look up which element this is. In this case, it would be plutonium. So it'd be PO. All right, so I mean we can do this with anything essentially that undergoes alpha decay. Well, not essentially. Anything that undergoes alpha decay, it's going to produce this right here, and it's going to produce a new element that is 2 protons less than what it was before, and 4 atomic mass units less than it was before. And then just to double check, 194 plus 4 is 198, 84 plus 2 is 86. All right, so beta decay. When we're talking about beta decay, this weird looking B, we're talking about the production of an electron, right? And it is a neutron turns into a proton and releases, ejects an electron. Yes. Okay, so uranium, so if we're going to write the equation for this, 237, uranium is 92, right? So we know that we're going to have a beta particle, right? 0, 1, E, or 0, -1, sorry, E. And everything has to match up. So it's going to be 237, right? Because 237 plus 0 equals 237. And then this is where it changes. Since the neutron turns into a proton, we're going to have more protons now. So 93 minus 1 equals 92. And it changed to neptunium, or however you said that, NP. I mean, we could do this for anything that undergoes beta decay. What's going to happen is this number is going to go up by 1, and you're going to produce a beta particle. That's the only change with beta decay. Positron emission. This is like beta decay, only different. So positron, you're going to produce 0 plus 1 E. This is an antiparticle. These things are really interesting. Okay, so the positron emission of silicon 26, silicon is 14. We know one of our products is going to be 0 plus 1 E, right? That's what a um, positron or beta plus, whichever one you want to call it, that's what is produced when it emits a positron. So once again, everything has to be the same. So 26, and then I believe we'll go 13 in this case. Yes, 13, and element number 13 is aluminum. So 13 plus 1 is 14, 26, 26 plus 0 equals 26. We're good to go.